Hello, I hope you are doing well. I came with another video regarding frequency estimation problem. I will introduce Capon method, which is one of the most important methods in spectral analysis. It can apply for frequency estimation of complex sinusoids. It also can be applied in context of array signal processing for direction of arrival estimation. The idea is so simple. It is based on filtering actually. If you want to opt a singleton from a signal, we only need a narrow bandpass filter. So we will have a filter here, a FIR filter with the weight vector W. W is a vector including impulse response, and the input vector is y and the output sample is yft. The input-output relation of the FIR filter or beamformer in context of array signal processing is W Hermitian y. The output power, actually the power of yft is expected value, absolute value yft power of 2. We can rewrite it expected value yft conjugate yft, and if we use this term we will have W Hermitian y Hermitian w, and finally we have W Hermitian expected value y Hermitian w, which is expected value y Hermitian is correlation matrix of the input vector. The frequency response of this filter is W Hermitian A omega. A omega is 1 minus j omega e minus j2 omega e minus j to m minus 1 omega. This is the frequency response of our filter, and in our desired frequency, the frequency response must be 1. I mean, we don't have any distortion in our desired frequency, so this must be 1, and actually this is the constraint of our problem here. And in other frequencies, actually there are interferences. We want to minimize the output power in other frequencies, except our desired frequency, we want to minimize the output power. So we have to solve this optimization problem to find the optimum weight vector, minimize W Hermitian or W subject to W Hermitian A omega equals to 1. This is a constraint optimization problem, and I have to use Lagrange multiplier to solve this problem. We can form the following cost function: J W equals to W Hermitian R W plus real part lambda conjugate A omega Hermitian W minus 1, and this can be written as W Hermitian R W plus lambda conjugate A Hermitian minus 1 plus W plus lambda W Hermitian A omega minus 1 over 2. Now we can take derivative J with respect to W. We compute gradient vector, and this must be 0. We have 2 RW plus lambda over 2 A omega plus lambda over 2 A omega. We solve this equation with respect to W. We have W equals to minus lambda over 2 R inverse A omega. Now I can use the constraint to compute lambda over 2. We have A Hermitian omega multiplies by W equals to 1. So A Hermitian W equals to minus lambda over 2 W Hermitian omega R inverse A omega equals to 1. That means minus lambda over 2 is 1 A Hermitian R inverse A. We have minus lambda دوم and we can substitute minus lambda دوم with this term. Finally, the optimum weight vector in Capon method equals to R inverse A W A Hermitian R inverse A W. And we can compute the output power of the filter and suggest a pseudo spectrum. Pseudo spectrum S omega is W optimum Hermitian R W optimum, which is the output power of our filter. And if we substitute W with this term, we can find A Hermitian omega R inverse A omega. This is the Capon pseudo spectrum, and we can use this spectrum to find the frequency of our signals. Actually, the location of peaks of this spectrum are our frequencies. Consider our correlation matrix is 2 minus J, J and 2. We can find R inverse 4 minus 1 2 plus J minus J and A Hermitian A omega R inverse A omega equals 1 J omega 2 J minus J 2 over 3 and A E minus J omega, and this equals to let's first multiply this 2. This is 2 plus J E minus J omega and minus J plus 2 E minus J omega. And now we have 1 multiplied by this 2 plus J minus J omega and minus J E J omega plus 2, and this term can be simplified. 2 plus 2 4 plus minus J E plus J omega minus E minus J omega, which is to J sinus omega, and this is equal to sinus omega plus 2 sinus omega. Our frequency is the location of peak of this pseudospectrum, the frequency that maximize this or minimize this term. To minimize this term, we only need set sinus omega equals to minus 1. So finally we have omega is minus p over 2, and we reach the final of this video. I hope you like it, and if you like it, press the like button and subscribe our channel.